quadratic functions in vertex form. So we're going to look at different kinds of transformations today. In 3.1, we focused on how a parent function changes by multiplying by some number a. So if a, the absolute value of a is greater than 1, then we get a graph that's narrower than the parent function. You'll see this additional language in here, vertical stretch and vertical shrink. This publisher does a kind of a change. So in Math 2, they use the terminology narrower and wider. And then when they transition to Math 3, they use the more mathematically accurate terms of vertical stretch and vertical shrink. So just to put a little nugget in your mind so you've seen it before. If the absolute value of a is between 0 and 1, we get a graph that's wider than the parent function. And if a is negative, then the graph opens down. So today we're going to talk about translations and vertex form. We're going to do some graphing. So what is a translation? Specifically, a translation is when I take a graph and I move it left, right, up, down, or some combination of those. Okay, so when I slide it around, that's a translation. A transformation includes any type of movement. So it could be a translation. It could be an a value that creates the graph to get narrower or wider. It could be when a is negative and it flips. So a transformation is all of them included. Let's do. Example 1, identify the vertex and the axis of symmetry for the function. We're doing a little bit of investigating here, so I'm going to navigate away from this and go to Desmos and just kind of look at some of the comparisons here. So this first one that we're looking at is g of x is equal to x squared plus 4. All right, so this is the original parent function. This is what we talked about earlier this week. F of x is equal to x squared. And the first problem that we're going to look at looks like this. Make that a different color, a little easier to see. G of x is equal to x squared plus 4. So we're talking about how does the graph change from the parent function to this new function if I just add 4 at the end. So hopefully you can kind of notice, and maybe if I move the screen around a little bit, it might be a little easier. Oh, there's a delay. Eek. Okay, stop. So my parent function crosses the origin at 0, 0. That's where my vertex is. And now I just have a vertex at 0, 4. So I've taken the whole graph and I've shifted it up 4. So if I add a number or I subtract a number on the outside, it's going to shift it vertically. I think the next one, is it x squared minus 2.5? Oh, you probably didn't write it down, huh? Let's go back and check. It is. X squared minus 2.5. Okay. So if I look at this graph, now when I have a minus number, I've moved from the parent function 0, 0 down 2.5. So if I'm adding or subtracting a number outside of, this is called the argument, it's causing a vertical shift. So we're going to go back and summarize that in our notes. I'm going to draw a sketch. It's not going to be super precise, but we're going to get an idea of some things here. Here's the parent function. And when we looked at the graph of f of x equals x squared plus 4, it shifted up 4. So this plus 4 at the end causes this graph to go up 4. And the question asked me to identify the vertex and the axis of symmetry for the function. So let's talk about that. The vertex is no longer at 0, 0, right? That point where the graph changes direction is now at 0, 4. And reviewing this idea of axis of symmetry. The axis of symmetry is the line that the parabola is symmetric about. For the parent function, the axis of symmetry is x equals 0. But that line is still the line that this new red function is symmetric about. So it's still going to be that the left side is a mirror image of the right side. It hasn't moved. When my graph shifts up and down, that axis of symmetry isn't going to change. It's still on the same line, still symmetric about the same line. So my axis of symmetry is going to be the equation x equals 0. It's always an equation. So it's always x equals some number. Don't just say 0. It's an equation of a line. And actually, the axis of symmetry is always going to be x equals some number, and that number is always the x coordinate of the vertex. Always. So if you can find the vertex, then you can find the axis of symmetry. Makes it easy. Keeps it simple. So then back when I graphed x squared minus 2.5 in Desmos, we noticed that that moved down 2.5. So that's a negative 2.5. The graph is still oriented the same way. It just gets shifted down. So the minus 2.5 outside the argument means that this goes down 2.5. Okay, so when I shift this whole thing down 2.5, now this new vertex here, remember vertex is always xy, so I go left or right 0, and then I go down 2.5, so I have a negative 2.5. Now the axis of symmetry is always x equals whatever the x value of the vertex is. It's just going to be x equals 0. This hasn't shifted. I've only moved up and down, so this line hasn't moved. It's still the same line of symmetry. Now there's a difference depending on where I add and subtract numbers. So you'll notice for A and B, I'm adding and subtracting something outside the argument. I'm using this term argument. The argument is whatever's happening to x directly. So because I'm squaring x, this is my argument here. So when I'm adding 4, subtracting 2.5, that's happening outside my argument. For these next two problems, C and D, I have something happening inside my argument. So I have a number added or subtracted inside the parentheses, and that's going to have a different effect on my graph. So write down C and D, leave some space like you did for A and B. I'm going to go back to Desmos and regraph those. Okay, so I have just the first one showing, so just x plus 3.2 quantity squared. And This now shifted the graph. Instead of going up and down, now it's going left, which seems a little counterintuitive because I have a plus sign in there. But that is correct. And I'm going to change the color of this one. When I subtract 3, I'm going to make that one disappear. When I subtract 3, it actually goes right. So if I add or subtract something inside the parentheses, inside the argument, it's going to shift left and right, but it's going to be counterintuitive to how you would think. So let's translate that to our notes. So parent function is at 0, 0. And this first one, x plus 3.2, actually went left 3.2. Try to hit that point there. Try that again. Looks kind of like it's more like 3. So this one actually moved left 3.2. So when looking at where is the vertex, now I'm going to go left or right and then up and down, right? Every point is x, y, so I go left first. So I go left negative 3.2 and then up or down 0. So now I have a change in x. My axis of symmetry is always x equals the x coordinate of my vertex. This time the axis of symmetry is going to change. I usually for my parent function have it at x equals 0. But now I'm going to have an axis of symmetry going straight through the center of the graph, which is going to be at x equals negative 3.2. X equals negative 3.2. I don't know why my negative is so high up. Let's try that again. Negative 3.2. The minus 3 inside the parentheses moved my graph to the right 3. 1, 2, 3. So then where is that vertex? So right 3 is going to give me 3 comma 0. For a parabola, my axis of symmetry is always going to be a vertical line going through the vertex. Now, when I look at different functions, it's not always a vertical line, right? It's just whatever line a function is symmetric about, if the function is symmetric. But in this case, it's going to be a vertical line. So I have x equals 3. These are just really kind of the building blocks that we've gone over here. So looking at one little piece at a time. How does the graph move? These covers all the different kinds of translations. Up, down, left, and right. It's going to be a lot easier for me to remember some rules to follow instead of graphing and having to make it up as we go every time. So I know I have an E here if you want to write E, but we're going to actually go back and do E after we write down all of this good information. So where it says the vertex form of a quadratic function, this covers all of the transformations. And we're going to learn them really, really good for quadratic functions this year, because next year this information is going to help us translate to a whole bunch of other kinds of functions. So if you would copy down all this section here, the vertex form of a quadratic function is f of x is equal to a times, parentheses, x minus h, n parentheses squared plus k. The vertex is always hk. A, just like we talked about in 3.1, if it's larger than 1, causes the graph to be narrow. If it's between 0 and 1, it causes the graph to be wide. And if it's negative, that means it just opens down. H causes a horizontal shift, but it's always backwards from what you would think. So you might want to put an asterisk there or highlight it or something, make it stand out. Because if I add H, it actually goes left, and if I subtract H, it actually goes right. And then K causes a vertical shift. If I add a number, it shifts up, and if I subtract a number, it shifts down. I'll give you a moment or two to copy that down. Then we'll go back and answer E. Okay, great. So now E gives us another example, but it's using what we learned in 3.1 about how to treat A, what A does to the graph, and what we just talked about in 3.2 with translations. And I'm looking at the entire problem and making, talking about all of the transformations. So, breaking it down piece by piece. The negative in front of the 0.5. The negative causes the graph to opens down. Right. It's technically called a reflection across the x-axis, but for today we're talking about it just opens down. And the 0.5, because that is between 0 and 1, the 0.5 is going to cause the graph to be wider than the parent function. Most oftentimes when I'm talking about transformations, I'm comparing it back to the parent function. Not always. If it says you're comparing it to something else, it'll be specific about it. The plus 1, whatever I do 2x, x is a horizontal axis, so whatever I do 2x left or right is going to happen inside those parentheses. So the plus 1, let's see, if I add a number according to my directions here, I'm going to shift left. So this is going to go left 1. And the minus 4 will make this go down. So anything that I add outside the parentheses, add or subtract, is going to be down if it's negative. So down 4. And I'm just using this as a map to determine that. So from this translation, I could come up with the new vertex. Just putting together a bunch of pieces that you'll see different problems to ask in your homework, right? So from the origin, if I go left 1, that's negative 1, and then down 4, that would give me a vertex of negative 1, negative 4. And the axis of symmetry is going to be always x equals the x value of my vertex. So x equals negative 1. So all of that describes the transformation. It also states the vertex and the axis of symmetry. putting together pieces. The next thing we're going to be doing is we're going to be doing graphing. Whoa, all that good stuff. Okay, so I will pause here and ask you to write down these steps. I think that they're helpful. All right. So we already talked about the steps to graphing in vertex form. Here they are for you again. Identify the vertex, plot and label the point. 2, sketch the axis of symmetry. 3, find 2 more points on the parabola. We're going to reflect those points, find 2 more points. We don't actually have to find 4. And then I'm going to draw the graph. So example 2, directions, sketch the graph of the function and the axis of symmetry. We will always draw the graph solid and the axis of symmetry dashed. In your Savas homework, if it asks you to draw the axis of symmetry, you'll have to draw it dashed as well. And there's an option on the menu to make it solid or dashed. So we're going to go with a more basic one and then maybe one that's got, some more moving parts. F of x is equal to parentheses x plus 2 quantity squared minus 3. So we were just talking about a quadratic function in vertex form is f of x equal to a times x minus h quantity squared plus k. Okay, and the function that I'm graphing here is x plus 2 quantity squared minus 3. I like to start with my vertex. So I'm going to kind of pick that out. The vertex is HK. And I just kind of lined them up here so they're right here and easy for us to find. So H is just going to basically be the opposite of whatever I'm doing to x. So I have x plus 2. H is going to be negative 2. That means I go left 2. And then K is minus 3. And so that's going to give me a K value of minus 3. So the one next to X is always the opposite of what it looks like. And K is always true. All right, so you've got some graph paper, so we're going to go ahead and let's see. So you have a vertex at -2, -3. So I always go left and right first. So left 1, left 2, and then down 1, 2, 3. Here's my vertex. Step 1, identify the vertex, plot, and label the point. Done. Step 2, sketch the axis of symmetry. My axis of symmetry is just going to be a dashed line that goes through the vertex. This is the equation x equals -2. And we're going to talk about 2 different methods on graphing. I want to start off with making a table, and we're going to talk about it and look at a pattern. And from here on, you can use the pattern, or you can make a table, or both. Okay. One of these points I already know. I already know that if I plug in -2, I get out -3 because that's my vertex. Cool. I want 2 more points so that I can really get a good idea of what this parabola looks like. The closer you can keep them to the axis of symmetry, the better. So I'm going to go 1 to the right and 2 to the right. So I'm going to pick, let's see, we already know what we get when we plugged in -2. So I'm going to plug in -1 and I'm going to plug in 0 to find 2 more points to kind of get an idea of what this parabola looks like. So I'm going to plug in -1 and 0. So I'm going back to my original equation, f of x is equal to x plus 2, quantity squared minus 3, and I'm plugging in -1. So I've just gone back to my original and replaced every x with a -1. This f of -1 is called function notation. We've seen it before. We're going to get good at it. We're going to see it more in this class and a lot more in future math classes. And it means the function of f evaluated at -1. These are like directions. This is not like do some math with this. This is I'm plugging -1 into this function. That's all that says. So the left-hand side is just going to stay f of -1, and I'm going to simplify the right-hand side using order of operations. Order of operations says I do what's inside the parentheses first when I can. -1 plus 2 is 1. 1 squared is 1. Minus 3 is -2. When x is -1, y, or f of x, is -2. So I plot the point. -1, -2. All right, I need another point. 2 points is not going to be enough for me to draw a parabola. I know it's enough for me to draw a line, but not for my quadratic function. So I'm going to also plug in 0. Zero plus 2 gives me 2. 2 squared is 4. Minus 3 gives me 1. So I put in 0 and I get out 1. So the coordinate 0, 1 will be up here. This is only a little piece of the parabola. And I can keep plugging in points. I can plug in 1, I can plug in 2. But I don't want to do all that work. Also, we can plug in points on the left-hand side to see what that looks like, but again, a lot more work. The table is like what takes the most amount of time. The easiest way to go about this now is just to take these points and reflect them across the axis of symmetry. Because I know that the right side and the left side are mirror images of each other. So if I have a point here, then I'm also going to have a point 1 unit away from the axis of symmetry over here. And I have a point up here at 2 units away from the axis of symmetry. I'm going to have another point here. So imagine if you were to fold this on the axis of symmetry, where would that other point lie? Let's just save ourselves a lot of work instead of plugging those in the table. And add these points. Yay. That'll give me enough to graph the parabola. All right, so let's talk patterns. Okay. So there's some shortcuts to graphing, which you can get good at, or we can always make a table. But I wanted to point them out to you. So when I'm graphing a parabola, we know that when I graph a line, we go back to graphing lines, whatever that slope is just continues over and over and over again, right? So if the slope is 1/3, I go up 1 over 3, up 1 over 3, up 1 over 3, and I continue that pattern. With a quadratic, I don't have the same number, but I have a new pattern. So if I go up 1, I go over. If I go over 1, I go up 1. Over 1, up 3. Over 1, up 5. And that pattern will continue as long as A is 1. So I'm going to write some notes about that. Here I have a difference of 1. To the next point, I have a difference of 3. And to the next point, I have a difference of 5. And that's going to be a pattern that I can follow anytime A is 1 or negative 1. So I have this pattern. Now, when I change and I have a different A value, the pattern is going to change. Just like when I have a slope of another number, I would multiply it by it. And you'll see this when we look at the next one. But if I were to have A of 2 instead of A of 1, everything would just double. So I usually have a pattern of 1, 3, 5. But if I have A as 2, then I double this. So 1 times 2 is 2. 3 times 2 is 6. And 5 times 2 is 10. So they just get multiplied, which is easier sometimes to use when graphing. We'll be doing it a lot, so you'll see it a few times. All right, we're going to repeat this work for the next problem. Questions on this before I move on? Things I can answer? It's a lot of little things, a lot of little pieces. Are we okay on the vertex and axis of symmetry? Because those are biggies. Yeah? Okay. The table is where the most work is. You seem like you can follow that. Is that all right? Yeah? Just plug them in and then sketch the rest. Okay. So the next one I'm going to do is b of x equals negative 2 times quantity x minus 1 quantity squared plus 1. And we're going to go through all the same steps again. Let's talk about some things in general that we can tell about this graph before we even get after the nitty gritty. This graph has an x squared. So I automatically know it's going to be a U shape. Is it going to open up or open down? Down. How do you know? Because that's got a negative, right, in front of the whole thing. Cool. So then we look at that 2. Is that 2 going to cause my graph to be more narrow or more wide? More narrow. It's going to be skinnier, right? It's going to go up faster. It's going to cause it to grow faster. Whatever I add or subtract to x always causes a horizontal shift. but it's backwards when I'm looking at x. So instead of, even though I have a minus 1 here, it's actually going to go to the right one. And this plus 1 outside of the parentheses causes a vertical shift. And since it's positive, it's going to go up 1. So let's put all those pieces together. I like to draw myself a little sketch just on the side so I don't forget that it goes down. When I recognize that it's a negative, I always just draw my little like U upside down so I don't goof it up on my graph. All right. And this is going to go right 1 and up 1. So my vertex, I go right 1, so that's positive 1, and then up 1, that's also positive 1. So up 1 over 1 is going to give me a vertex here. Okay, so now I need to pick points for my table. This is how you could pick any x value you want. But in order for it to be something that's going to fit in my window, I want to pick something close to the axis of symmetry. Speaking of, let me draw that in. It goes through the vertex, and it's just x equals 1, whatever the x value of the vertex is. I just want something close to this. So here I am at 1. I don't want to pick 1 because I already know it's 1, 1. I could pick 2 and 3, or I could pick 0 and negative 1. I just want something close. I'm going to pick two x values. I'm going to go for 0 and negative 1. I like plugging in small numbers. That works for me. If you're like, no, I'm not plugging in a negative, you can pick 2 and 3. That's okay. I know when I plug in 1, I get out 1, so I have that point.
What are you teaching?
Graphing problem. They should learn it this year because they're going to need to know it next year again, right?
Very much.
Good job dressing up.
Thanks. I did every day of the week.
Proud of you.
Bye, Miss Thompson.
Bye. See you Monday. Okay. So if I plug in 0, what does that look like? G of 0 minus 1 quantity squared plus 1. Zero minus 1 gives me a negative 1 squared. Oh, I'm plugging in. Oh, yeah, that's right. Order of operations is I have to do exponents first. So negative 1 squared gives me a negative 1 times negative 1, which is positive 1. And I get an output of negative 1. I want to make sure that you can use your order of operations. So would you please take x equals negative 1 and plug it into the g of x function and evaluate, find the next point. You should be able to tell if you plugged it in correctly. This should be in this vicinity, right? If it's like in a different quadrant, then it's wrong. So go ahead and plug in negative 1. See how it goes. Focus on those order of operations. So the point, when I plug in negative 1 into my function, I'm going to get out negative 7. So negative 1 down 7. 1, 2, 3, 4, 5, 6, 7. Luckily, it's going to fit on my graph. Yes. It's what? Oh, thank you. There you go. Sorry about that. So when I plug in -1, I get out -7. Gives me the point -1, -7. And I plot that right down here. We've got to practice that to get good at it again. Now, to save myself the work from plugging in more points over here into a table, I'm just going to map them over. This is the axis of symmetry. Whatever distance occurs on one side is going to be replicated on the other side. So this point right here, 0, -1, is 1 unit away from the axis of symmetry. So when I reflect it over, I'm going to have a point at 2, -1. And then similarly, this point down here in quadrant 3 will get mapped over here. Make sure this distance is equal from the point to the axis of symmetry. All right, we said this was going to open down, and it does, so we didn't goof there. That's good. Now, if we go back and we look at this pattern, you'll notice that the distance between the vertex and the next point is 2, and the next distance is 6. And that's just double what it would be if I had 1, 3, 5, right? So if I had 1, 3, 5, but if A is 2, then I double it, I double it, I double it. So you can see a distance here of 2 and a distance here of 6. All right, last one. Go ahead and copy that graph down. This one won't take so long. All right, the graph represents the quadratic function. Write the function in vertex form. So we have two main things that we need here. I need A, and I need the vertex to be able to fill in. You're going to write this so many times that you're going to know it so well. It is the vertex form of a quadratic function. The easiest part is the vertex. So this vertex down here, -2, -5, that's my HK. So I'm going to plug that in. I'm going to leave a space for my a, and then I'm going to have x minus h. H is already minus 2, so I'm going to actually have a minus negative 2. That's okay. I'll clean it up in a second. And then k is minus 5. The equation is minus, and I have a negative, so I have minus negative 2. And I still need this a value. There's an easy way and there's a hard way to do this. The easy way is from the vertex, I'm going to go 1 point to the left or 1 point to the right and up to the next point. So 1 point to the right or 1 point to the left, not more, not less. And I want this distance. That distance is a. It opens up, so I know it's positive. When I clean this up, I get f of x is equal to 3 times parentheses x plus 2, quantity squared, and then minus 5.